So here we go, and that's screencast number 6. And I'm mentioning the numbers because it makes sense to watch them in order. Let's start with this one. This is titled as from first principles. Let's write it here. First principles to rules. And that's going to be the conversation we're going to have here. So in order to keep videos short, what I have done, I have already answered the first question that you've seen already, potentially by now. But essentially, the question is asking you, let's put a question, find the derivative of the following functions from the first principles. And first principles is what you have on your formula booklet, and it looks like that. So you're going to have to go and apply the original definition of the derivative, right? So that's what I've done down here for the f of x equals x squared. And then we're going to move to do together the g of x is equal to x to the power of 3. And let's find a few ways to kind of work it out. So g of x is equal to x to the power of 3. We need to apply the first principles. So to find the first derivative of g of x, we're going to have to calculate the limit when h goes to 0 of g of x plus h minus g of x over h. At this point, I would suggest you to pause the video and go ahead and work it out by yourselves. And then if you need some help, you can always kind of come back to it. Yes, please go ahead and do so. I would just carry on with solving the question. Now, so the first thing we have to do is to substitute x plus h into the g of x. So don't forget the limit here, because that's what we always calculate. And then I'm going to have x plus h to the power of 3 minus g of x, which is going to be my x to the power of 3. All right, let's make this one shorter, which is going to be just x to the power of 3 over h. And what I need to do now, I'm going to have to expand the bracket. When h goes to 0, and I need to do x plus h to the power of 3. Now you might just say, oh, I don't remember that. Well, what am I going to do? I'm not going to multiply through brackets. No, you won't going to multiply through brackets. If you don't remember, then you're going to do Pascal's triangle. So this is level 0, right? This is level 1. This is level 2. You want the level 3 because it's to the power of 3, right? So it's going to be 1, 3, 3, 1, right? And these are the coefficients. So all I know now is I'm going to have 1 times x to the power of 3. So I'm going to have x to the power of 3 plus 3, and then x squared h plus 3 again from Pascal's triangle, x h squared plus h to the power of 3 minus x to the power of 3. Here we go, over h. At this point, as we always do exactly the same thing, we're going to have to cross things out. So what we're going to cross out here is the x to the power of 3 with the x to the power of 3. And then the next move we have to do is going to have to be the final one. Always, 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 we're going to have to move into the factored form. Factor h at the top. So the first derivative of x is going to be limit when h goes to 0. And then what we have left at the top is this part, and this part. So that's going to become h times 3x squared plus 3xh plus h squared over h. The reason we factor the h is to basically cross it out, and that means it's going to cross out, and then whatever is left is going to be able to be calculated, because then we have just the limit when the h goes to 0 of 3x squared plus 3xh plus h squared. Well, that's the substitution kind of like, step. Because if you substitute h equal to 0, then what we get is that becomes 0 and that becomes 0. So the final answer is going to be 3x squared. So how does this move us from the first principles into rules? So if we have a look, so let's make a little table, and this is the function is here, and then the derivative is here. So when the function was the x squared, the derivative was the 2x. And when the function was x to the power of 3, the derivative ended up being 3x squared. So if you're able to kind of like, carry on and do the x to the power of 4, and if you want to convince yourselves, please do, and use Pascal triangles to calculate the coefficients and so on, you're going to end up with 4x to the power of 3, and if you do one more, x to the power of 5, then you're going to end up the derivative being 5x to the power of 4. And if you pay attention on the patterns between this column and this column, then you actually realize that every time I have a form of x to the power of n and I want to find the derivative, right, and we write it like that or as a dash, or the other notation is going to be the d of x of n over dy, over dx, dy over dx, but my y is the x to the power of x to the power of n. Then the derivative, it becomes, the power comes at the front, and then times x, and then the power goes by 1 down. So if you chalk back here, x squared becomes x to the 1, 3 becomes 2, 4 becomes 3, and so on. So that becomes 4x to the power of n minus 1. This is now a rule for derivative, and this is of course the same. So let's include it all the same. So this is now the rule. So how do I use that? Well, if you end up having an h of x, which is x to the power of 9, then you can deduce straight away by using that rule, which is called power rule. And it's called power rule because it involves the powers, what we do when we have powers. Then the derivative of h of x is going to be equal to 9x to the power of 8. And if I want to find that specific point at 3, no, I'm not going to calculate it. I'm going to be clever. So because I can sometimes to be clever. So at x equals 5, then I just substitute, and that's going to become 9 times 5 to the power of 8. And I wasn't that clever after all, because I'm not going to calculate the 5 to the power of 8 without the calculator. But that is the power rule.